So the first part of this exam is to determine to show the Lewis relation. And the way we're going to do that is by first defining the Nusselt number NU and the Sherman number as H. And we're going to say that both these values are equal to a certain expression, an arbitrary expression. So we're going to say an arbitrary value A times the Reynolds number raised to the arbitrary value B times the Prandtl number raised to the arbitrary value C. So that's going to be our equation for the Nusselt number, and then our Sherman number is going to be an arbitrary value A times R E raised to the B, so the Reynolds number raised to the B power arbitrary value, and the Schmidt number as H raised to the C. And we also know that the Nusselt number is equal to the heat transfer coefficient H times the diameter divided by the thermal conductivity, and we know the Sherwood number is related to the mass transfer coefficient Kc times diameter divided by the concentration diffusivity from A to B, so dAB. And we know that the Prandtl PR divided by SC, SC, the Schmidt number, is going to be equal to 1 over the Lewis number, LE. And we know that 1 over the Lewis number is equal to dAB over alpha, which is going to be our thermal diffusivity. And we know that alpha is equal to our thermal conductivity divided by the density times the heat capacity. So K divided by rho Cp. And now we can go ahead and plug that in. So now 1 over LE, the Lewis number, is equal to dAB rho Cp divided by K. So 1 over the Lewis number is equal to the concentration diffusivity from A to B times rho, which is the density times the heat capacity divided by the thermal conductivity. And since all this stuff is equal to one another, we can go ahead. We can go ahead and set these expressions equal to or 1 over the Lewis number. So we go ahead and say our heat transfer coefficient times diameter divided by K divided by our mass transfer coefficient, Kc, times diameter divided by the concentration diffusivity from A to B is equal to our concentration diffusivity from A to B rho Cp, so density times heat capacity divided by our thermal conductivity. And at this point, we can go ahead and simplify the left-hand side of the equation, and we could say that, let's just simplify this here. So heat transfer coefficient divided by the diameter divided by K times dAB over Kc d. You can go ahead and cancel out the diameters, and now we're left with H times dAB over K times Kc. So our heat transfer coefficient times concentration diffusivity from A to B, all divided by our thermal conductivity times the mass transfer coefficient, Kc. So we would say now H dAB over K KC is equal to DAB rho CP divided by K. And we have here that DAB over K and DAB over K are both on the left hand and right hand side of the expression. And for moist air specifically, one over the Lewis number is going to be equal to 1. So now we could say that DAB over K equals 1 over rho Cp. So the concentration diffusivity from A to B divided by the thermal conductivity is equal to 1 over the density times the heat capacity. So now we're having that relationship. We go ahead and plug that relationship into our expression here, and we get the heat transfer coefficient divided by density times heat capacity times the mass transfer coefficient equal to the density rho Cp, density times heat capacity divided by density times heat capacity. And now we can go ahead and simplify this expression, and we get H over Kc equals rho Cp. And this is going to be our Lewis relation. And just to say it over again, the heat transfer coefficient divided by the mass transfer coefficient equal to the density times the heat capacity is going to be our Lewis relationship.